Okay, we're at the top of page 24, which is the beginning of the organic chemistry unit. And contrary to popular opinion, this is not the hardest unit. The reason why a lot of people think this is so hard is because this unit is covered at the end of the year when you're pretty much pooped out. And not only that, what makes it worse is the fact that because it's at the end of the year, most teachers have very little time to cover this material. Now, if you find this material easy, if you feel confident with it, then go with this review as presented here, which is limited to 3 pages. On the other hand, if you feel like you need more time with this unit, then what you should do is go to the extended unit, and I spend more time developing it, teaching it, and then you can come back to this as the review. All right. When I see organic chemistry, right away the C in organic reminds me of the carbon, which is the central element in organic chemistry. Organic chemistry is the chemistry of carbon compounds, in other words. And what you want to remember back when we covered this in bonding, you want to remember that the carbon by itself, unbonded, would have this pair with 2 singles as far as electrons are concerned. But on the other hand, when the carbon is bonded, remember you have to open up these electrons. And now you have 4 equivalent electrons, unpaired electrons, that could bond in single bonds, double bonds, triple bonds. In the case of CH4, if you recall, which is one of those top 6 molecules you ought to know, you have 4 single covalent bonds. You'll remember CH4 as the methane, the very symmetrical molecule. It has a tetrahedral shape, and for that reason I've written here, don't be square, be tetrahedral, man. And that has to do with the fact that when you first look at this, you're thinking maybe that the hydrogens are going to arrange in this square-like pattern and giving you like a flat molecule. But on the contrary, because of really things you don't have to know about for the Regents, turns out that the CH4 doesn't have a square or flat shape. It actually has a tetrahedral shape. And you'll learn more about that in your AP Chem or College Chem course, how the electrons end up hybridizing, how the orbitals want to be as far away from each other as possible, all that stuff. You may have mentioned it in a honors chemistry course or some kind of institute course where they mention VSEPR, but right now I'm just going on and on. The bottom line is that what we end up with is a symmetrical molecule. All right, so if any of that stuff that I just heard is unfamiliar, do not worry. All right, the main point here is tetrahedral. Whether you find this funny or not, don't be square, be tetrahedral, man. This is something a friend of mine used to say all the time, but I threw in the man to spice it up. And tetrahedral is a symmetrical shape. That's the main thing you want to know. And as you recall, symmetrically shaped molecules, which applies to most organic compounds that consist of symmetrically shaped molecules. Symmetrically shaped molecules are nonpolar. They are nonpolar or non-dipoles. You might recall that we would represent that as this egg-like figure with a positive and a negative charge in the center, indicating that there is no positive or negative side to such molecules. And since water is polar, most organic compounds are insoluble in water. Remember, water is like this. Water is polar, and since they are different, like does not dissolve like here. And also for most organic compounds, in line with the fact that they're nonpolar, that they are insoluble in water, you also want to remember that they are non-electrolytes. Remember, in order to be an electrolyte, the substance has to produce ions in aqueous solution. So most of them are non-electrolytes, meaning no ions. No ions in water. No ions in AQ, if you will. Also, you might want to put these together, 1, 2, 3, and 4, also related to the fact that they are non-polar symmetrical molecules, is the low melting points. Since the attraction between one non-dipole and another non-dipole will be a weak force known as dispersion forces. So this is because of the weak London dispersion forces, LDFs. Okay, and then the last two properties are related to the fact that when covalent compounds, as what's illustrated here with the carbon atom in the center, see that black carbon atom? You might recall the ball and stick model that we had some time ago with the black carbon, my black shirt, to remind you of that. And here's the carbon in the center, and the covalent bonds projecting from that at an angle of 109.5, which is what that tetrahedral angle is all about. But you don't really have to know that. That just came with this illustration. All right, and so the point is that since in a chemical reaction, bonds have to be broken, and then atoms rearrange and new bonds are formed, since these covalent bonds are strong, when you have strong covalent bonds, it's going to take a lot of energy to break those bonds initially. So these reactions typically will have high activation energies, higher than that of inorganic compounds, and because of that, they'll react slower than inorganic compounds. So that's the last 2 points here. They react slower than inorganic compounds, and it's because they have high activation energies. All right, that's pretty much it for the top panel here, as far as I can remember. So why don't we erase and then continue to cover organic chemistry, at least the first page here on it. And you're going to need your reference table, so we can refer to your reference table, so you can refer to table P and table Q to continue this review. So let me turn down there with this. Okay, looking at table P and table Q, first of all, to the left, table P. Remember, you're always going to have this on the exam, particularly on the Regents, right? Because that's what we're preparing for. So table P is a table of organic prefixes. We're going to need this table to give you the first piece in the name of an organic compound, because what we do is we count the number of carbon atoms in the chain, the longest continuous chain, and if there's one carbon atom, as in the case of methane, it would be, if it's a one carbon alkane, it would be methane, and then there's 2 carbons, F, prop, but, pent, etc. So let me show you how that works in conjunction with this table here, table Q. Table Q is called a homologous series of hydrocarbons, and I like to think of these just as families. The families of hydrocarbons, which are compounds that consist only of hydrogen and carbon. As you see in these examples here, all you see is carbon and hydrogen, carbons and hydrogens, etc. And these hydrocarbons can be divided into 3 families, all right, in general. And we have the alkanes, the alkenes, and the alkynes. All right, and in this example here, this molecule, or this compound, would be named ethane because it's a eth, 2 carbon alkane. So eth here, the prefix is because it has 2 carbons. And the ane is because it's an alkane. And the reason what makes this an alkane is the single bond, because alkanes have only single covalent bonds. So only single bonds in them. On the other hand, the second molecule is referred to as ethene because, again, it's a 2 carbon alkene. What makes an alkene is the presence of this double bond here, which looks like an equal sign. And that is 2 pairs of electrons that are being shared, giving us 4 electrons in total. All right, so alkenes have only one double bond. The rest of them will be single. And then after that, the alkynes, these 3 lines here, refer to a triple bond. And that would be, if you want to elaborate, if you want to play the tic-tac-toe, would be really 6 electrons or 3 pairs. So the alkynes have 1 triple bond, triple covalent bond, of course. All organic compounds have covalent bonds. And so that's how you can distinguish them. So we have ethene and ethyne, the Y in the ending. So the ending, or the suffix, if you will, depends on what family of hydrocarbons the compound belongs in. All right, and then let's make another division here between alkanes and alkenes. The alkanes, because they have single bonds, have the greatest amount of hydrogen per carbon. So we say they are saturated, SATD, with / hydrogen. Not to be confused with saturated solutions, which we had covered in Table G, where you have aqueous solutions saturated with different solutes. All right, this is saturated with hydrogen. And then the last 2 families, the alkenes and the alkynes, compared to the alkanes, have less hydrogen, so they would be unsaturated. All right, and now let me show you how these general formulas work, because that might be a little confusing, to show you how all of these compounds within a family fall into the same general formula. I mean, you can do it with this example here, but maybe there's too much here to deal with. So let's play out an example, a fresh example, right below this. We have a little space, I think. Yeah. So suppose we have n equals 5, where n is the number of carbon atoms. So if n equals 5, and we're talking about an alkane, then for an alkane it would be CnH2n plus 2, where n again is the number of carbons. So 2 times 5 plus 2 would give you 12. So it would be C5H12 if it's an alkane. On the other hand, if it were an alkene, it would be CnH2n, so the number of hydrogens is twice the number of carbons. It would be C5H10. And if it were an alkyne, it would be twice the number of carbons minus 2. And so 2 times 5 is 10 minus 2 gives you C5H8. Now, as far as the naming, let's practice that. Since each of these have 5 carbons, then in the naming we would have to have the pent prefix. And so the first one would be pentane. The next would be pentene. And the third would be pentyne. And well, of course, we'll have more practice with this later, but it's good to make a note of it right here. All right, so now let's continue with this, and I wanted to go over the rules, the IUPAC rules, for naming hydrocarbons, and examples that are more complicated than these. Let's talk a little bit about that now, and that's what you'll find in the next panel here. Okay, notice IUPAC, which stands for the International Union of Pure and Applied Chemistry, and these are the guys that give us the rules for naming hydrocarbons and their derivatives. So what I'll do is, let's just illustrate by example here. We have identify the longest continuous chain of carbon atoms and name it, indicating the number of carbon atoms and the type of bond between them. So first of all, we have the longest continuous chain. Should highlight that. The type of bond is important. All right, so how about we have something like this? 1, 2, 3, 4. Let's put another carbon here if you want. So, and what I'll do is I'll just keep the hydrogens out of this. And so to get the longest continuous chain, you count carbons from left to right or right to left. 1, 2, 3, 4 going down. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. So no matter which way you go, the longest chain here is a 4-carbon chain, and we'll call that the parent on which everything else is attached. So since it's 4 carbons in a row, and you could put in the hydrogens later, with single bonds, so prefix but and ane. So that would be our parent chain. And now we have attached to this parent chain, to make it clearer, a carbon with 3 hydrogens, which is called not a methane but a methyl group. So the attachments, most common attachments are alkyl groups which end in YL. Since this is a 1-carbon attachment, we call it a methyl group. If it were a 2-carbon attachment, it would be an ethyl and propyl, etc. So this attachment here is called a methyl group. And so when we put this together in this case, we would have methyl butane for the name of this compound. All right, we can put that name right here. Methyl butane. 2 separate words. Okay, now let's make up a larger molecule so we can apply rules 3 and 4 to that. So let's count like this. Let's put a here. We can put them both in the same, really doesn't matter. Let's put one up and one down. I've written over the notes there, but no problem, we could read through it. Now, again, we're going to do the longest continuous chain as before. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That's pretty long. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So 7 is the longest chain no matter what. So let's loop that. And we have single bonds here, so we're going to call that 7. If you go to your prefix table, it's going to be hept because they're single bonds. It's an alkane, so we're going to call this parent chain a heptane. And as before, the attachments here, we'll call this attachment here a CH3. You could draw it like that. Or you could draw the hydrogens if you want, and we'll make this one here also CH3. So we have, in this case, 2 methyl groups. So on a heptane chain, and that's where rule 3 comes in, where you want to indicate how many of each attachment is present using the di, tri, or tetra prefixes. So in this case, this would be a dimethyl heptane. Now, the 4th rule is we have to indicate where these methyl groups are because they could change positions. So, in counting, we want to make sure that we choose the lowest numbers possible. So let me show you what I mean by that. If we count from left to right, we'd have 1, 2, 3, 4, 5, 6, 7. If we count in the other direction, from right to left, 1, 2, 3, 4, 5, 6, 7. Now the reason why I'm doing that is because we have to choose what numbers to give to these attachments. In counting from left to right, the methyl groups would be a 4, 1 on carbon 4, 5, 1 on carbon 5, so dimethyl, heptane. But in the other direction, it would be a 3, 4 dimethyl. And since 3, 4 adds up to less than 4, 5, you have to choose the lowest number as possible. And so the name of this compound correctly would be 3,4-dimethylheptane. But don't expect anything this complicated, all right? And the last point I want to bring in is about this preference. So let me add a space here. I do have some space at the bottom, so let's do that. So the last of the rules here in naming hydrocarbons and their derivatives, let me illustrate with this. It says that note, each attachment gets numbered. Well, we covered that already with the 3,4-dimethyl. Both methyl groups get a number. But point B is more important now. A double or triple bond takes preference in numbering over the positions of any of the attachments. So double or triple bond, a multiple bond, takes preference. Let me show you what I mean. Suppose we had a 5-carbon chain, 1, 2, 3, 4, 5. And suppose we had a methyl group here, CH3, and I'll just erase, or we'll draw in the hydrogens, so we can focus on the carbon backbone. Now let's put a double bond here. Now you could number this from, again, left to right as 1, 2, 3, 4, 5. Or from right to left, 1, 2, 3, 4, 5. Now the question is, what's more important? Giving the double bond a 1 position or giving the methyl group a 2 position? And since IUPAC tells us the double bond takes preference, then we're going to number from left to right, which is going to force the methyl group to be in the 4 position. And so you're going to name this as a 4-methyl and a 1-pentene. All right, and what a number of students do is to try to satisfy this rule is they count from both ends. So it would be a 1-pentene at the same time with 2-methyl, but you can't do that. Once you've decided to count from one end, you can't reverse in naming it. So giving the lowest number to the multiple bond, which in this case is the double bond, forces the methyl group to be numbered on carbon number 4. Okay? Then, before we finish, on your notes there, you should see that to the right of this text box, there are the first 4 members of the alkane family, which on the slide here, I decided to do it horizontally to save space. And what you should note here is that as we go from methane to ethane to propane to butane, and as they continue to get longer and longer, there is a consistent difference here of a CH2. So to go from methane to ethane, all you have to do is add a CH2. To go from ethane to propane, again, add a CH2. And from propane to butane, add a CH2. So there is this consistent difference between consecutive members in these families, and that's why they're called a homologous series. Maybe it'd be easier to see like this. CH4 plus CH2 gives you C2H6. And if you add another CH2 to this, you would get C3H8. So again, here's your consistent difference, and we call that the increment. And another thing I'd like you to note is let's work a little with these formulas while we're here. And we said that for the alkanes, the general formula is CnH2n plus 2. Let's go forwards and backwards just for more practice. So suppose they say it's C10. They want to know what the H value would be. Well, then it would be 2 times 10 plus 2, which is 22. That's your H value. C10H22, which by the way would be called decane. Now going backwards on this, Suppose they had given you C unknown, H 30. So what I'm saying, in this case, you'd have to set the 2n plus 2 equal to 30. So 2n plus 2 equals 30. Subtract the 2 from each side and you get 2n equals 28, and divide by 2 and you get 14. But you don't have to name any compounds with more than 10 carbons, so I have no name for you on that. Okay, so that's the end of this page. Let's continue this organic review. And again, if you think you need more, then go to the extended review either after or whatever you like on organic.